All right, so taking a look at exam number 1 from 2015, looking at 6A, and the question asks, which compound in each pair is more acidic? So the more acidic compound here, basically we're looking for a difference between these compounds and looking at our factors that affect acidity. So the difference here is hybridization state. So that carbon right there is sp3 hybridized, and this carbon is sp hybridized. Now, why does that matter? So the question says, which of these is more acidic? Right? Which is more acidic? You can look at the reactivity of the starting materials, or you can look at the stability of the products to understand the reaction. So the question I have is, do you know what the conjugate base is? If I add a base to either of these, it's going to take an H. What does the conjugate base of this look like? For each of these, it's different. So for this one, what hybrid orbital is that lone pair in? It is in an sp3 orbital, which of course is long and skinny. What hybrid orbital is this lone pair in? It's in an sp orbital, which is shorter and rounder. Because this is shorter and rounder, it's closer to the nucleus. That makes this lone pair more stable. Right? That makes this a worse base, less reactive base than this, because these are farther away from the nucleus, more reactive. What that means on the front end, though, is that this is more acidic than this. So anytime a reaction takes place, you have one of two things: reactive starting materials and or stable products. So neither of these products, neither of these starting materials are reactive, I would say. CH bonds aren't polar bonds. And even actually this bond right here is technically a stronger bond than this CH bond. There's more orbital overlap here than here. But that difference is very small. So the difference between how strong this bond is versus this is very small. It's different, but it's smaller. But the stability of this versus this is much greater. So this is actually more acidic because of the resulting product is more stable. All right, taking a look at 1C from the 2016 exam 1. So 1C asks for us to circle the nucleophile. So basically this is a question asking, do you know what the definition of a nucleophile is? So are nucleophiles electron rich or electron deficient? They're electron rich, so you're going to want to find the best nucleophile here. That one has a negative charge. That's the most electron rich, it's the most reactive nucleophile. So that's the nucleophile. And everybody else is electrophiles, actually. Aluminum itself has an empty p orbital. It's sp2 hybridized. There's an electrophile there. Carbocations are electron efficient, not a full octet, not a full octet here either. Oxygen with a plus charge. The hydrogen's actually electron efficient, not the oxygen. The hydrogen's the electrophile here, not the oxygen. Formal charges, right? Lewis dot switchers lie sometimes. So either way, that's the nucleophile. So let's take a look at the next one, which is going to be about examining the most stable resonance structure. And you're never going to believe the overriding rule here, of course, is the octet rule. All right, taking a look at 1D. The question here asks, circle the most stable resonance structure below. Which one of these is going to be the most stable? So a couple things you need to look for. Charges and octet rule. And octet rule is more important. So as we evaluate these, let's look for octet rule first. Does everybody in this molecule have a full octet? Sure does. Does everybody in this molecule have a full octet? Sure don't. So we can eliminate that, right? There's a carbocation right there. That's not a full octet. If I have something with a full octet, that's automatically better than anything without a full octet. Octet rule is most important. Full octet? Yep, full octet. All right, so these last three, A, C, and D, all have full octets. Now we look at charge. This has a carbon with a negative charge. There's a carbon with a negative charge, and the charge is a long ways away. Long ways from the plus charge. Carbon with a negative charge close to the plus charge, and a carbon with an oxygen with a negative charge. What's better with having a negative charge, oxygen or carbon? Oxygen is more electronegative, so that means it'd be more likely to have a negative charge. The best, most stable resonance structure, therefore, would be this one. So it's all about the octet rule, and then about looking at electronegativity and which one would be more likely to have a negative charge.
You can't do that.
So number 6A on 2016 asked you to draw the conjugate base for the molecule below. Using arrows, draw one potential resonance structure for the conjugate base. So first you need to say, okay, this is the acid part. So these electrons are going to leave or react to the base. So we have those electrons will go to the oxygen. You'll make an H plus and an O minus. That's the first thing. You got to draw the conjugate base. So this is the conjugate base of this molecule. And then it says, draw one potential resonance structure for the conjugate base. So again, this comes back to that question of even this oxygen is what hybridization state? What's the hybridization state of that oxygen? It is sp2 hybridized. Why? Because then one of its lone pairs can be in a p orbital. And then one of those lone pairs can be part of the resonance system. So again, here, even when it's been deprotonated, guess what? It's still sp2 hybridized. Right? Because that means one of those lone pairs, again, is in a p orbital. So then it can be part of this, because it's next to a pi bond. That's why it's doing this. So the resonance structure will look like those two electrons going there. The pi bond breaks. We make a new pi bond between oxygen 1 and carbon 2. We broke the pi bond between 2 and 3. And the lone pair goes on carbon 3 now. 2, 3, 4. One common error I see that people will try to do. They'll try to move electrons on carbon 4. But you can't do that. Because carbon 4 all along the way, even though they're not drawn in, of course has 3 bonds to hydrogen. Carbon 4 has no pi bond electrons or lone pairs. It can't be part of resonance. Right? Remember, in resonance you only move pi bond electrons or lone pairs. So carbon 4 is just along for the ride. You can't move electrons towards it. It doesn't have a pi bond or lone pairs. Yeah, so you can start. You could have done, right. If you wanted to, you could have done. This is not the only way to do this for that resonance. If I redraw this guy, one, two, three, four. You could have done. I'm just going to say I'm going to show the electrons going there. I'm going to draw a resonance structure like that. You could have done, now, is it a better resonance structure? Let's hold on and see what it looks like. So 3 got electrons, 2 lost electrons. There's a carbocation there. So it's still 1, 2, 3, 4. Is this a valid resonance structure? Yeah, it works. It's fine. It's less likely. There's more charges. It's less likely, right? Because everybody here has a full octet. This one has a carbocation that doesn't have a full octet. But could this happen? Sure, you could do that.
So it doesn't matter.
No, if I just asked for all resonance structure and not the best, this would be fine, for sure. All right. Good question. So let's examine some chair conformations, and let's think about something. These 1,3 diaxial interactions. It's 1,3 diaxial interactions. So what they are is essentially when carbons or when substituents are in the axial position, right, because these are all axial up right now. What happens is big things don't want to be axial because big things end up getting in each other's way, and we call that a 1,3 diaxial interaction, meaning they're 1, 2, 3 carbons from each other. So these groups are axial and they're in each other's way. So we call that a 1,3 diaxial interaction. It's better, that's why it's better to have bigger groups equatorial. So if we were to take this thing and do a ring flip, let's number our carbons. All right, if we did a ring flip, carbon 1 gets pulled down, carbon 4 gets pulled up, so the head becomes the foot becomes the head. So this is 1, 2, 3, 4, 5, 6. So what was on carbon 1, right? When we do chair conformations, we're not actually breaking any bonds, right? We're just flipping, right? We're chair flipping. So 1 has a tert butyl group. Is that up or down? Up. So on the ring flip, is it still going to be up? Yes. But if it's axial on the ring flip, it's now going to be equatorial. So it's still in carbon 1, and it's equatorial and up. Carbon 3 had a methyl that was up. Right, that's a methyl. All right, it's up and axial. On carbon, now once you do the flip, it's going to be up still, but now it's going to be equatorial. Carbon 5 is also has a methyl that's up and is axial. On the ring flip, it's going to be up and equatorial. So which one of these is more stable? That would be this, with all the big group, especially this group, the tert butyl group, equatorial. It's the best way to do it. Got to be able to draw these chair structures really well. You're going to have to do that a couple of times. So the diaxial interactions are 1, 2, 3 carbons away from each other. 1, 2, 3. These axial groups on the same side, top or bottom, running into each other. That's what they call those are high energy interactions. That's why they'd rather be equatorial. So 2016 exam, version B, bonus 1. You're given a sugar, hexose sugar, and asked to turn this into a wedged and hatch version. So let's just draw that's what I would draw right away. 6-membered ring with an oxygen in it. So sugars, we have an oxygen there instead of a carbon. Numbering system is super important. Doesn't matter how you number it as long as you're consistent. Start the oxygen 4, 5, 6. 1, 2, 3, 4, 5, 6. So now you got to make sure you have everything that's on carbon 2 that's here onto here. Now the question is, how do I know what's wedged and what's hatched? It actually doesn't matter as long as you're consistent. So the way I like to look at things, it's just the way I do it. I like to see whatever's up, I like to think of that as wedged. And whatever is down, I think of it as hatched. Can you do it the other way? Can you do exactly the opposite? Sure, doesn't matter. But that's how I like to do it. So it's not right or wrong, right? You could draw everything that's down as wedged if you want to. I like to do it as hatched. As long as, right? So the key here is this OH on carbon 2, what is its relative position to the ethyl OH on 6. Are they cis or trans? Like think the OH on 2 versus the ethyl OH or the methyl OH on 6. They are what to each other? They are trans. So it doesn't matter how you do it, as long as those two those relationships need to be the same. So I'll draw the way I like to draw it, and I'll draw the other way too, so you can see it. So I like to think of this as down, 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 up. That's one way you can do it. Another right answer I'll leave the way it is. Could be 1, 2, 3, 4, 5, 6. I could have it be it's hard for me even to even think about doing it this way. It makes me confused. Both of them are fine. Both of them are right answers. They're actually mirror images of each other. They're enantiomers to each other, which is like we're going to talk about next. So yeah, either way is fine. So I'm just arbitrarily choosing. The key is be consistent. Notice this thing on 6 and 2 are always trans. Doesn't matter. You just gotta be consistent. The things that are all on the same side need to all be wedge or hash. And that's just the key. So here's 3 molecules. Let's rank these. We're gonna rank them A, B, C, and then let's add another one to the mix. Let's add this. Let's rank them from lowest boiling point to highest boiling point. Lowest to highest. So after much debate and wrangling and gnashing of teeth, we decided that A was the highest boiling point and D was the lowest. Now why? For A, it can do hydrogen bonding, which is a very strong intermolecular force. It's not a full bond, but it's a really strong electrostatic potential interaction. So that's going to make the boiling point much higher. Something like D, right? So we're always kind of looking for polar bonds. OH bonds, right? Hydrogen bonding. Hydrogens bond to heteroatoms, O to O, nitrogen, phosphorus, sulfur, and those kind of things. Those are really polar bonds. Another thing we're looking for is just regular polar bonds that aren't hydrogen bonding. So a carbon bond to an oxygen, that could be a polar bond. So that creates a dipole, which creates a part of the molecule that's more electron rich than another part. So right, opposites attract. That can create stronger intermolecular forces. So this aldehyde would be the next highest boiling point. Then this 1, 2, 3, 4 butane would be the next much lower boiling point than either of these two, because this has no polar bonds, but it could still do London dispersion forces where it can kind of stack. And then this version 1, 2, 3, 4, 5. This 1, 2, 3. Propyl 2,2 dimethyl propane. Right, can't stack as well. So this is actually going to have the lowest boiling point for sure. Even though so both of these don't have polar bonds.
Is that what you would call it, as London dispersion forces?
Van der Waals, London dispersion forces, something like that. Yeah. Good. So acids and bases. How do I decide if they're reactive or not reactive? All right, the first thing you need to know to be able to answer that question is, do you know the definition of what an acid is or what a base is? So let's go to the biggest definition possible, the most general definition. What's the most general thing about acids that we know? It's always going to come back to about electrons. An electron, are acids electron deficient or electron dense? Acids, are they deficient or dense in electrons? They're deficient. They're electron deficient. Bases, are they electron dense or electron deficient? electron dense. Right? So reactive acid is the more electron deficient, the more reactive the acid. Right? So one example could be, here's a boron. There's two borons. Which one's the more reactive acid? The BF3 or the BCl3? Which one do you think is going to be the more reactive acid? First, you got to ask, where's the most, in both cases, where's it electron deficient at? Where's the electrophile at? No. The borons. Which one, where's the electrophile at? The electrophile, right? Acids, right? So remember, the bigger thing, one level up from acids is all acids are, we call them electrophiles. Right? Lovers of electrons. One level up from bases, they're called nucleophiles. Lovers of nucleuses. So, to understand reactivity of an acid, you realize acids are electron deficient. So the more reactive acid is going to be more electron deficient. So you have boron in both these cases. The boron is the most electron deficient atom in each case. You agree on that? Which of these is more reactive? BF3, BCl3? BF3, why? Why does fluorine pull electrons better? It's more electronegative, right? It's more electronegative, right? Don't forget, it's a higher up in the column, it's still more electronegative than stuff below it. Size is a factor, but it's not the only factor, right? So this pulls more, so that's more electron deficient. So this is a more reactive acid. You could think of, another example could be, between these two. First of all, here's two molecules. Where is it electron deficient at? Which atom is electron deficient? In this one, which atom is electron deficient? Nope. Nitrogen's bonded to a hydrogen. Who owns the electrons? Who's more electronegative, nitrogen or hydrogen? So just because there's a plus charge, does that mean it's electron deficient? Remember we said Octet Rule, and then the Lewis dot structures sometimes lie to us. So where is this actually electron deficient at? On the hydrogens. Where is this electron deficient at? It's not the oxygen. It's the hydrogen. All right, so which one is more reactive? Oxygen. Why? Oxygen is more electronegative. It's going to hog more electrons. It's going to make this a more polar bond than this bond would be. Because nitrogen is more electronegative. That's a more polar bond. That makes this more electron deficient than a nitrogen would. Two things, right? Be careful. Just because there's a plus charge doesn't mean that atom's electron deficient. Right? Be careful with that. Next thing, right? You're looking for the most reactive spot. That's electron deficient. That's how you know it's more reactive acid. This is more, right, being pulled more by a more electronegative atom than this one. That makes this H more reactive. All right, so now the other side of it, how do I know if it's a reactive base? A reactive base has more electrons available to react, right? So you can think about it a couple ways. So think about the things we know. We know about hybridization state. We know about resonance. We know about size, electronegativity, and induction. So let's pick one. Pick one of those five. Now I'll make an example up that talks about base reactivity. Induction. Cool. I can do that. Which of these two is the more reactive base? More reactive base. So we look at it, what's the difference? So everything's the same except what? This has a chlorine, this has a bromine. Well, what's the difference between chlorine and bromine? Size. But this has nothing to do with, it seems to me, right, if you had both these atoms, where's the nucleophile at? What atom is the most electron rich in both of these cases? In these molecules. Where's the electron rich atom? The oxygen. How does the chlorine or bromine size have anything to do with that? Does it? Usually size, you have to be either literally bonded to whatever you're talking about or stable, right? That's kind of stable by yourself. So I don't think size is going to work here. So what else is different? So chlorine and bromine are certainly different. Electronegativity. Which one's more electronegative, chlorine or bromine? Chlorine. So chlorine's going to pull electrons this way, right? By pulling electrons that way, what's that going to make that base? Is it going to make it more reactive or less reactive? Makes it less reactive, right? Because, right, bases we judge based on how electron dense they are. A more electron dense base, the more reactive it is. If chlorine can pull away electron density better than bromine, that's going to make this oxygen less reactive than this one. So the more reactive base is this one. Right? So don't forget the definitions. Acids are electron dense. A more reactive acid is more electron dense. Bases are electron dense. A more reactive base would be electron dense. Acids are electron deficient. A more electron deficient acid would be more reactive.